In the last two lectures, we defined the notion of valuation. We studied some examples of valuation, and for number fields, we proved that an Archimedean valuation is given by embedding of a number field in complex numbers and then taking the modulus there. So, any Archimedean valuation of a number field is equivalent to one of these. Today, we are going to prove a similar result about non-Archimedean valuation. So, we saw an example of a non-Archimedean valuation given by fixing a prime of the ring of integer, prime ideal of the ring of integers. Today, we are going to prove the converse, that if you take a non-Archimedean valuation, then there is an associated prime and it fits in with the example that we saw before. But before moving on, we will prove a property of a non-Archimedean valuation which makes it what is called an ultrametric. So, non-Archimedean valuation satisfies something stronger than triangle inequality. So, we will prove that first. So, let this be a non-Archimedean valuation on a number field K. Then we can, what we do is we consider alpha plus beta to the power n for some large enough n. Now, you can use binomial expansion to write this as n going from 0 to n, a n alpha to the n minus n, beta to the n. A n's are some binomial coefficients. I do not really care too much about them. Okay. Yeah, maybe I will put it as this. This is less than or equal to, by using the usual triangle inequality. Right. So, now I consider a equal to 1 in the definition of the valuation. Okay, so this is a n times alpha to the n minus n, beta to the n. Okay, so normally I would have power to of a to apply triangle inequality, but I am not doing that. Now, as this valuation is non-Archimedean, I know that valuation of these integers is less than or equal to 1 for all n and capital N. Okay. All right. What this means is that the right hand side. So okay. So I'll rewrite the whole thing, taking into consideration this inequality. This is less than or equal to summation n going from 0 to n, valuation of alpha to the n minus n, beta to the n. Okay. All right. Which is another, so this is less than or equal to, there are capital N plus 1 terms, and I can write max of alpha beta to the power n, right. So, this is clear that each of this quantity, so as alpha to the n minus n, beta to, sorry, this should be small n here, is less than or equal to max of alpha beta to the power n. Okay. All right. And so, taking nth root, what we get is alpha plus beta is less than or equal to n plus 1 to the 1 by n max of alpha comma beta, right, valuation of these two. Now, n plus 1 to the power 1 by n, that goes to 1, right, n plus 1 to the 1 by n goes to 1 as n goes to infinity. something that you learn in the very basic analysis course. Hence, we get valuation of alpha plus beta is less than or equal to max valuation of alpha, valuation of beta. Okay. So, this is stronger than triangle inequality, right. This is stronger than triangle inequality. So, you start with triangle inequality plus the assumption that your valuation is non-Archimedean, and you get something stronger than triangle inequality. Now, here is a very here is a small lemma. If valuation of alpha is not equal to valuation of beta, then valuation of alpha plus beta is actually equal to max. So, not only is less than or equal to, but equality is attained. Okay. And why is that? Well, you apply, so here is a proof. What you do is you write alpha as alpha plus beta plus minus beta, and so you get valuation of alpha is less than or equal to max of valuation of alpha plus beta, comma valuation of minus beta, but that is same as valuation of beta. So, this is max valuation of alpha plus beta, valuation of beta, right. And this on the other hand is less than or equal to max of valuation of alpha, valuation of beta, right. And the same thing for similarly for valuation of beta. Valuation of beta is less than or equal to max valuation of alpha plus beta, comma valuation of alpha, which is less than or equal to max valuation of alpha, valuation of beta, right. And hence we get so one of them has to be an equality, which means that valuation of alpha plus beta is equal to max valuation of alpha, valuation of beta. Okay. All right. Okay. So, this property is called ultrametric, as I said. All right. So that is a very nice property of triangle inequality. One curious fact about this is that in the metric space, maybe you can take this as an exercise if you have not seen this before. In the metric space given by non-Archimedean valuation, every triangle is isosceles, okay, which means that in any triangle there are two sides that are equal. So that's some nice, something curious that you don't see in usual geometry, but you see in non-Archimedean geometry. So that's why people find it strange at first, but non-Archimedean metric is actually much easier to work with. So let this be a non-Archimedean valuation on a number field K, then there is a non-zero prime ideal P and a constant okay, let me write it down and then I need some sort of slight extra assumption, and a constant C bigger than 1 such that valuation of alpha is C to the power minus m for all alpha in K minus 0, where m is such that p to the m is the largest power of p dividing the ideal generated by alpha. Okay. So, m is in general an integer. So, you can allow minus powers. It means that when you take prime factorization of this fractional ideal, the non-zero fractional ideal, you will have p appearing to mth power. Okay. Alright. So, here I need an extra assumption that this is non-constant, right, i.e. this is not equal to 1 for all, maybe let me write it like this. There exists alpha in K minus 0 such that valuation of alpha is not equal to 1. Okay. So, if it is 1 for everything, then it does satisfy the definition of being a non-Archimedean valuation, but we do not consider those kind of valuations anyway. All right. Yes, so how do we, I mean, one difficulty is how do we go about finding the prime ideal? All we are given is a valuation on a number field, right. There is no mention of a prime ideal. So, we are given a non-Archimedean valuation this on K. We have to find a prime ideal from this, right. Okay. So, we are given some analytic property and from that we have to find a prime ideal. So, how do we, something algebraic. So, how do we go about it? Well, we start with, so let alpha be in K minus 0, and therefore, it is a it's an algebraic number, right. Actually, we can do, I mean, as we know, we can always work with rings of integers, and then any element of K is a ratio of two such elements. So, we can use that and that is what we are going to do. So, there exists f of x which is x to the m plus a1 x to the m minus 1 plus a2 x to the m minus 2 and so on up to am equal to in zx such that f of alpha is equal to 0, right. That is the definition of being an algebraic integer. Okay. So, what do I know? I know that alpha to the m plus a1 alpha to the m minus 1 and so on up to am is equal to 0, right. Now, what do I know from this? I know that valuation of alpha to the m, a1 alpha to the m minus 1 and so on up to am is equal to 0. But on the other hand, valuation of alpha to the m plus a1 alpha to the m minus 1 and so on up to am is less than or equal to max of valuation of alpha to the m, valuation of a1 alpha to the m minus 1 and so on up to valuation of am, all right. Okay. So, if valuation of alpha is bigger than 1, then we know that valuation of alpha to the m and so on up to am is equal yeah, okay, that is not quite what I want. Okay, in any case, let me, yeah, I kind of made a mess of this. I do not want to start with 0. What I wrote is not wrong, but let me redo this. Okay, so let me kind of scratch this part and let me redo this. Do not worry about that. So my claim is that valuation of alpha is less than or equal to 1. So, if valuation of alpha is bigger than 1, then I want to get a contradiction, right. So, what I will do is I will write alpha to the m as minus a1 alpha to the m minus 1 minus a2 alpha to the m minus 2 and so on up to minus am. This will tell me that valuation of alpha to the m is equal to valuation of a1 alpha to the m minus 1 plus up to am, but this is less than or equal to max valuation of a1 alpha to the m minus 1 and so on up to valuation of am, but valuation of ai is less than or equal to 1. So, I can rewrite this as valuation of alpha to the m is less than or equal to max valuation of alpha to the m minus 1, valuation of alpha to the m minus 2 and so on up to 1, which is less than or equal to valuation of alpha to the m minus 1, which is hence what we get is valuation of alpha is less than equal to 1. That is a contradiction, right. Therefore, valuation of alpha is less than or equal to 1 for all alpha in OK. That is what we proved, right. So, that is what I was after, and then instead of using the equality alpha to the m equal to something, I use this. I mean, you can get a contradiction this way as well, but it is kind of this way of writing it is much neater. Okay. All right. So, what I am going to do next is I am going to, oops. Yeah. Okay. Yeah. So, what I am going to do is I am going to define P to be valuation to be all alpha in OK such that valuation of alpha is less than 1. Okay. So, here are claims. P is a non-zero prime ideal in OK. So, this is how I find my prime ideal, right. I told you that the problem is how do I find my prime ideal starting with this analytic data. So, this is what the prime ideal, this is what I claim to be my prime ideal that I am seeking, that I am looking for. So, first of all, why is it non-zero? Okay. All right. So, there exists alpha in K minus 0 such that valuation of alpha is not equal to 1, right. So, I can always, so there exists beta in OK such that alpha times beta is inside OK, right. Now, if valuation of alpha is less than or equal to 1, then valuation of alpha beta, sorry, strictly less than 1, because I know that it is not equal to 1, so I can write strictly less than. Then this is less than or equal to valuation of alpha, I mean, okay, it is equal to, sorry, it is equal to valuation of alpha times valuation of beta, but I know that valuation of beta is less than equal to 1. So, this is valuation of alpha which is less than 1. So, hence there exists alpha beta in OK such that valuation of alpha beta is less than 1. On the other hand, if valuation of alpha is strictly bigger than 1, right, then valuation of alpha inverse is less than 1, and we do the same thing. We use the same argument as above. Okay. So, hence P is non-zero, therefore, P is non-zero, which means that as a set P is non-zero. 0 is there, but there are, i.e. there exists alpha in OK minus 0 such that alpha is also in P. Okay. The second thing is why it is an ideal. What is the definition of being an ideal? So, if alpha beta is in P, then alpha plus beta, if you take valuation of that, this is less than or equal to maximum of valuation of alpha, valuation of beta, which is less than 1, right. Hence, alpha plus beta is also, sorry, not mod, but only. Hence, alpha plus beta is also in P, right. So, P is an additive group. This is why this kind of thing, getting a prime ideal using this inequality works only for a non-Archimedean metric whenever you have the stronger triangle inequality. If you just have the regular triangle inequality, you will not be able to say that valuation of alpha plus beta is less than 1. So, that is one property. And if x belongs to OK and alpha belongs to P, then x times alpha, if I look at valuation of this is equal to valuation of x, valuation of alpha, which is less than equal to 1 times valuation of alpha, which is less than 1. So, hence x alpha is also in P. Hence, P is an ideal. Next, I want to show that it is a prime ideal, right. What does that mean? If alpha beta are two elements in OK such that alpha beta belongs to P, then valuation of alpha beta is less than 1. But on the other hand, this is equal to valuation of alpha, valuation of beta, right. So, at least one of them has to have valuation less than 1. So, hence either valuation of alpha is less than 1 or valuation of beta is less than 1. Hence, alpha is in P or beta is in P, which is what it means to say that it is a prime ideal. Okay. All right. So, amazingly, starting with this valuation, some analytic property, we have gotten an algebraic object out of it. All right. So, what I am going to do next, I still need to show that valuation of each element is given by the divisibility property in terms of P, right. So, what do I do for that? So, what I do is I let pi be an element which is in P but not in P square, right. OK is, we know that OK is a Dedekind domain, and so P is not equal to P squared, and so I can always find something like this, right. So let alpha be any element of OK minus 0, right. Then if I look at, so if I consider the fractional ideal, okay, and let P to the m be the largest power of P dividing alpha, okay. Consider the fractional ideal alpha by pi to the m. If I write this as A1 by A2, where A1 and A2 are ideals in OK, then what do I know? That then both A1 and A2 are co-prime to P. I mean, of course, I choose them in the reduced form, right. I don't let A1 and A2 have common prime ideal factors. Okay. So what do I get? I can then, yeah, so I can then get, so we can, so this is all Chinese remainder theorem or the corollary to it. We can find beta 2 in A2, beta 2 prime to P, right. So we can always do that, and then beta 1 I can write as beta 2 alpha by pi to the m, right. This is in A1, right. And now I know that beta 1 and beta 2, neither of them are in P. Hence, if I take valuation of beta I, this will both be 1. Right. And so what we get now, hence valuation of alpha is same as valuation of pi to the power m, right. And so we can take C to be valuation of pi inverse, right. Therefore, valuation of alpha is C to the minus m, and this was for any alpha, and pi was chosen independently of alpha, right. And so that is how you get what you want, right. Okay. So, yeah, so any non-Archimedean valuation is given by a prime ideal, right. So now let me do the following then. So if this is a valuation on K, a number field, then we can consider completion of K with respect to the metric induced by valuation. So we saw that valuation induces a metric, and you can take completion of with respect to that metric, okay. And this is not a new process, we have already seen this before. So let me do an example. If you take K equal to Q, and this is the usual right as a real number, then completion of Q with respect to metric induced by this by this valuation is R. This is what we learn in analysis course. If you take Q and you take its completion with respect to the usual metric, you get real numbers, right. Now here is a new concept perhaps for you. So if you take the p-adic metric, right, this is p to the minus m, if x is equal to p to the m, a by b, where a and b are integers co-prime to p, then completion with respect to this metric is QP, field of p-adic numbers. Okay, so this is perhaps a new field for you, but in fact analysis on this p-adic completion of Q is much easier. So next time we will look at p-adic numbers in much more detail, and we will give different different descriptions of QP. So this is a very analytic description of QP in terms of completions. So you can think of them as Cauchy sequences, or you can think it in terms of inverse limits of z mod p to the n and then inverting p, or you can think it like some sort of power series. That is more explicit, but perhaps not as useful theoretically. So yeah, we will stop here today. Thank you.